Hello aspirants, welcome to Magic World of Physics. In this video, we're going to discuss about some questions from classical mechanics part which is asked in various exams like GATE, NET, Barc, CHEST. Hope this video will be helpful for your coming Barc exam 2026. Without any further delay, let's get started. So here the first question is, a particle moves in two dimension on the ellipse x square plus 4y square is equal to 8. At a particular instant, it is at the point x comma y is equal to 2 comma 1 and the x component of its velocity is 6. Then the y component of its velocity is dash. So here an equation is given, that is x square plus 4y square is equal to 8, and x and y coordinate is given, that is x is equal to 2 and y equal to 1, and also vx is given as 6. So here we need to find out the vy value, that is the y component of the velocity. So the solution is x square plus 4y square is equal to 8. So differentiating this, we get 2x dx by dt plus 4 into 2y into dy by dt is equal to 0. That is 2x dx by dt plus 8y dy by dt is equal to 0. Substituting the value of x is equal to 2 and y equal to 1 in this equation, we get it as 4 dx by dt plus 8 dy by dt is equal to 0. And dx by dt is written as vx and dy by dt is vy. So that is 4vy plus 8v 4vx plus 8vy is equal to 0. Substituting the value of vx is equal to 6 here, we get it as 24 is equal to minus 8 vy, that is vy is equal to minus 3 meter per second. So this is the velocity y component. So the next question is, the number of degrees of freedom of a rigid body in d space dimension is. The options are 2d, 6, d into d plus 1 by 2, d factorial. So the solution is, for a rigid body of d dimension, the degrees of freedom is equal to translational degrees of freedom plus rotational degrees of freedom. And we know as it is mentioned as d dimension, so the degrees of freedom for translational is d, and rotational degrees of freedom is d into d minus 1 by 2. Changing this, we can write as 2d by 2 plus d into d minus 1 by 2, that is 2d plus d square minus d by 2, that is equal to d square plus d by 2, that is d into d plus 1 by 2. So the degrees of freedom is equal to d into d plus 1 by 2. So the next question is, the Lagrangian of a particle moving in a plane is given in Cartesian coordinates as L is equal to x dot y dot minus x square minus y square. In polar coordinates, the expression for the canonical momentum PR is dash. So here we need to find the canonical momentum PR. So in this question, L is given as x dot y dot minus x square minus y square, and we can rewrite it as L is equal to x dot y dot minus of x square plus y square. In polar coordinates, x is equal to r cos theta and y is equal to r sin theta. Differentiating this, we get x dot is equal to r dot cos theta minus r sin theta theta dot, and y dot is equal to r dot sin theta plus r cos theta theta dot. Substituting these values in equation number 1, we get as L is equal to r dot square sin theta cos theta minus r square sin theta cos theta theta dot square plus r dot r cos square theta theta dot minus r dot cos square theta theta dot. From here we can calculate PR, that is PR is equal to dou L by dou R dot, that is equal to 2r dot cos theta plus r theta dot into cos square theta minus sin square theta, that is equal to r dot sin 2 theta plus r theta dot cos 2 theta. The next question is, the parabolic coordinates theta and eta are related to the Cartesian coordinates x comma y by x is equal to theta eta and y is equal to half into theta square minus eta square. The Lagrangian of a two-dimensional simple harmonic oscillator of mass m and angular frequency omega is dash. So here we need to calculate the value of Lagrangian. X and y are given. So the solution is, for a 2D harmonic oscillator, T is equal to half m x dot square plus y dot square, and V is equal to half m omega square x square plus y square. So the Lagrangian L can be written as half m x dot square plus y dot square minus half m omega square into x square plus y square. That is, so in the question itself it is given as x is equal to zeta eta and y is equal to half into zeta square minus zeta square. Differentiating this, we get x dot is equal to zeta dot eta plus zeta eta dot, and y dot is equal to zeta dot minus eta dot. This can be rewritten as half m into zeta square plus eta square a into eta dot in the square a plus eta dot in the square a minus 1 by 8 m omega square into zeta raised to 4 plus eta raised to 4 plus 2 zeta square eta square. This is equal to half m zeta square plus eta square a into zeta dot square plus eta dot square minus 1 by 8 m omega square into zeta square plus eta square the whole square, and this is equal to half m into zeta square plus eta square into eta square plus eta dot square minus 1 by 4 omega square into zeta square plus eta square. So the answer is B. The next question is, a particle of mass m moves inside a bowl. If the surface of the bowl is given by the equation z is equal to half a into x square plus y square, where a is a constant, the Lagrangian of the particle is dash. So here z is given and we need to find the value of Lagrangian. Here z is given so that we can use the cylindrical symmetry, that is x is equal to r cos y, y is equal to r sin phi, z is equal to half into a x square plus y square, that is equal to half a r square. And we know Lagrangian is half m x dot square plus y dot square plus z dot square minus mgz. So this can be marked as equation number 1. So here we can calculate x dot as r dot cos phi minus r sin phi phi dot, and y dot is equal to r dot sin phi plus r cos phi phi dot, and z dot is equal to ar r dot. And the equation 1 can be rewritten as L is equal to half m into 1 plus a square r dot square plus r square phi dot square minus g a r square, because we know x dot square plus y dot square is equal to r dot cos phi minus r sin phi phi dot the whole square plus r dot sin phi plus r cos phi phi dot the whole square. This is equal to r dot square cos square phi plus r square sin square phi dot square minus 2r r dot cos phi sin phi phi dot plus r dot square sin square phi plus r square cos square phi dot square plus 2r r dot sin phi cos phi phi dot, that is equal to r dot square plus r square phi dot square, that is x dot square plus y dot square plus z dot square is equal to r dot square plus r square phi dot square plus a square r dot square, that is equal to r dot square into 1 plus a square plus r square phi dot square. So substituting all these values in equation number 1, we get the option D as the right answer. This question is, the equation of motion of a system described by the time-dependent Lagrangian L is equal to e raised to gamma t into half mx dot square minus v of x is dash. So here we have given a Lagrangian and we need to calculate the equation of motion, that is L is equal to e raised to gamma t into half mx dot square minus v of x. That is, here the generalized coordinate is x, so that we need to calculate dou L by dou x dot, that is e raised to gamma t into mx dot. Then dou L by dou x is minus dou v by dou x into e raised to gamma t. Then the equation of motion can be written as d by dt of dou L by dou x dot minus dou L by dou x is 0, that is d by dt of e raised to gamma t into mx dot plus dou v by dou x into e raised to gamma t is equal to 0, that is mx double dot into e raised to gamma t plus mx dot gamma into e raised to gamma t plus dou v by dou x into e raised to gamma t is equal to 0. Mx double dot plus m gamma x dot plus dou v by dou x into e raised to gamma t is equal to 0. Then mx double dot plus gamma mx dot plus dou v by dou x is equal to 0. That is, the option A is the right answer. So the next question is, the Lagrangian of a particle of charge E and mass m in applied electric and magnetic field is given as L is equal to half m v square plus Ea minus v minus E phi, where A and phi are the vector and the scalar potential corresponding to the magnetic and electric field respectively. Which of the following statement is correct? Here we have given a Lagrangian and we need to calculate we need to check whether the statement is correct or wrong. So here the first option says that the canonical conjugate momentum P is mv. So we need to check whether it is right. For that, P is equal to, P is equal to dou L by dou V, that is half M into 2V plus EA, that is MV plus EA. So this proves that in the option it says that the canonical conjugate momentum P is MV, but we calculated it as MV plus EA. So that option A is wrong. Then coming to option B says about the Hamiltonian. So we need to check whether the Hamiltonian is right. So for that, we know L is equal to half mv square minus e5 plus e into I dot b. We can write v means the velocity, so we can write the v square as x dot square plus y dot square plus z dot square. So the next step can be written as L is equal to half m x dot square plus y dot square plus z dot square minus e5 plus e into ax x dot plus ay y dot plus az z dot. From here, we can calculate the Hamiltonian as the general equation for Hamiltonian is p q dot minus L. We know q is the generalized coordinate and p is the corresponding canonical conjugate, canonical momentum. So here the generalized coordinate is x, y, and z. So the corresponding momentums are px, py, and pz. So the equation can be rewritten as x dot bx plus y dot py plus z dot pz minus half m v square plus e5 minus e into ax x dot plus ay y dot plus az z dot. From here we can calculate px, py, and pz. That is equal to px is equal to dou L by dou x dot is equal to mx dot plus eax. Py is equal to dou L by dou y dot, that is equal to my dot plus eay. Pz is equal to dou L by dou z dot is equal to mz dot plus eaz. Substituting these equations in the above equation, we can rewritten the Hamiltonian as x dot into mx dot plus eax plus y dot into my dot plus eay plus z dot into mz dot plus eaz plus e5 minus e into ax x dot plus ay y dot plus az z dot minus half mb square. So this is equal to m into x dot square plus y dot square plus z dot square plus e into ax x dot plus ay y dot plus az z dot minus half m v square plus e5 minus e into ax x dot plus ay y dot plus az z dot. So from here e into ax x dot plus ay y dot plus az z dot term get cancelled. Then the remaining terms are m x dot square plus y dot square plus z dot square minus half m b square plus e5. The first term mx dot square plus y dot square plus z dot square is mv square. So this can be like mv square minus half mv square, that is half mv square. So this is half m into x dot square plus y dot square plus z dot square plus e5. So this is equal to half mv square plus e5. That is we know the conjugate momentum p is equal to mv plus ea. This is calculated in the option A. So from here we can write v is equal to p minus ea by m. So substituting the value of this in half mv square plus e5 equation, we can write it as half m into p minus ea by m the whole square plus e5. That is h is equal to half into p minus ea the whole square by m plus e5. So we can say that the option B is also wrong. We need to check the option C is correct or wrong. So the option C says the Lagrangian L remains unchanged under a Gauss transformation of the potential. So we need to check if the potentials, that means the scalar and the vector potential, if it undergoes a gauge transformation, whether it causes a change in L or not. So we are assuming that if we are changing the phi and a, that means the scalar and vector potentials as phi dash and a dash. Yes, if phi is undergoing a gauge transformation, it can be rewritten as phi dash. That is, phi dash is equal to phi minus dou f by dou t. And a dash can be written as a plus del phi, where a dash is the gauge transformation of the potential A. Phi dash is the gauge transformation of potential and A dash is the gauge transformation of the vector potential. Substituting these values in the Lagrangian changes from L to L dash. That is, L dash is written as half mv square plus E into A dash dot V minus E into phi dash. Then we can substitute the value of A dash and phi dash in this equation. So this equation can be written as L dash is equal to half mv square plus E into A plus del F dot V minus E into phi minus dou F by dou T. That is equal to half mv square plus E into A dot V plus E into del F dot V minus E phi plus E into dou F by dou T. That is equal to half mv square plus E into A dot V plus E into df by dt minus E dou F by dou T plus E dou F by dou T minus E phi. Because del F, we know del F is dou F by dou x I cap plus dou F by dou j cap plus dou F by dou z k cap. And V is dx by dt I cap plus dy by dt j cap plus dz by dt k cap. So from here we can calculate dou F dot V, that is equal to dou F by dou x into dx by dt plus dou F by dou y into dy by dt plus dou F by dou z into dz by dt. We know df by dt is equal to dou F by dou x into dx by dt plus dou F by dou y into dy by dt plus dou F by dou z into dz by dt plus dou F by dou t. From here, we can write df by dt minus dou F by dou t is equal to dou F by dou x into dx by dt plus dou F by dou y into dy by dt plus dou F by dou z into dz by dt. So we can write, we know the left hand side dou F by we know that df by dx into dx by dt plus dou F by dou y into dy by dt plus dou F by dou z into dz by dt is del F dot V. So this del F dot V can be written as df by dt minus dou F by dou t. Substituting these values, we write the equation as we write the value of L dash as half mv square plus E into A dot V plus E into df by dt minus E into dou F by dou t plus E into dou F by dou t minus E phi. So that this can be written as L dash is equal to L plus E into df by dt. So that we can from here we understood that the L dash and L is not same, because the option C says that the L remains unchanged even after the gauge transformation of this potential, but this proves that L dash is not equal to L, because that is because the L remains L doesn't remains unchanged. That means L changes, that means the Lagrangian changes after the gauge transformation of the potential. So the option C is also wrong. Then coming to the next option, D says that under the gauge transformation of this potential, L changes by the total time derivative. That means the D option says that if we had done the gauge transformation of the potentials, the L changes by L dash, that the L dash and L differs by an amount of total time derivative. That is, L dash is L plus E into dou F by dou T. And this is true in this case, because here we calculated L dash as L plus E into df by dt. Then we know df by dt is the total time derivative of a scalar function. So that the D option says that the under a gauge transformation of the potential, L changes by total time derivative, and this proves that the D option is right. So the next question is, a double pendulum consists of two point mass m attached by strings of length L as shown in the figure. The kinetic energy of the pendulum is dash. So here we need to calculate the kinetic energy of this double pendulum. So we know that here it is given that the double pendulum is of the length L, and it makes an angle theta 1 and theta 2. So the distance from the first end to the mass m can be noted as x1, and the other distance can be noted as x2. x2 is a distance from first end to the second mass, that is x2, and the distance to the first mass is x1, and the distance to the second mass is x2. From this figure, we can write x1 as E is equal to L sine theta 1, x1 dot is equal to L cos theta 1 into theta 1 dot. And from here, x2 is equal to x1 plus L into sine theta 2. So that x2 is equal to sine theta 1 plus L sine theta 2. That is x2 dot is equal to L cos theta 1 dot plus L cos theta 2 dot. And from here we know y1 is equal to L cos theta 1, y1 dot is equal to minus L sin theta 1 into theta 1 dot, and y2 is equal to y1 plus L cos theta 2, and y2 is equal to L cos theta 1 plus L cos theta 2, and y2 dot is equal to minus L sin theta 1 dot plus L sin theta 2 dot. And we know the kinetic energy T is equal to half m x1 dot square plus y1 dot square plus half m into x2 dot square plus y2 dot square. That is equal to half m into L square cos square theta 1 dot square plus L square sin square theta 1 dot square plus half m into L square cos square theta 1 dot square plus L square cos square theta 2 dot square plus 2 L1 L2 cos theta 1 cos theta 2 theta 1 dot theta 2 dot. L square sin square theta 1 dot plus L square sin square theta 2 dot square plus 2 L1 L2 sin theta 2 theta 1 dot theta 2 dot. And this can be written as this is equal to half ml square theta 1 dot in the square plus half ml square theta 1 dot square plus theta 2 dot square plus 2 theta 1 dot theta 2 dot into cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. So this can be written as this is equal to half ml square theta 1 dot square plus half ml square into theta 1 dot square plus theta 2 dot square plus 2 theta 1 dot theta 2 dot cos of theta 1 minus theta 2. So this can be written as this is equal to half ml square into 2 theta 1 dot square plus theta 2 dot square plus 2 theta 1 dot theta 2 dot cos of theta 1 minus theta 2. So this is the solution. So the next question is the Lagrangian of a particle of mass m moving in one dimension is given by L is equal to half m x dot square minus bx, where b is a positive constant. The coordinate of a particle x of t at time t is given by dash, where c1 and c2 are constants. So here we need to calculate the equation of motion, that is d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. That is d by dt of mx dot plus b is equal to 0. That is mx double dot plus b is equal to 0. That is mx double dot is equal to minus b. This can be written as d square x by dt square is equal to minus b by m. That is dx by dt is equal to minus b by m into t plus c1. And this can be written as x is equal to minus b by m into t square by 2 plus c1t plus c2t. Is calculated after integrating the differential equation. The next question is a particle moves in a potential V is equal to x square plus y square plus z square by 2. Which component of the angular momentum is the constant of motion? Here we know that Lx is equal to m into y z dot minus zy dot, Ly is equal to m into zx dot minus xz dot, Lz is equal to m into xy dot minus yx dot. From here we can calculate fx is equal to minus dou v by dou x, fy is equal to minus dou v by dou y, fz is equal to minus dou v by dou z. And we know we know that v is equal to square plus y square plus z square by 2. And from here we can calculate fx is equal to minus 2x, that is equal to mx double dot, and fy is equal to minus 2y, that is equal to my double dot, and fz is equal to minus z, that is equal to mz double dot. And differentiating Lx, Ly, Lz, we can write dLx by dt is equal to m into y z double dot minus zy double dot. The equation of fx, fy, fz, we can calculate x double dot is equal to minus 2x by m, y double dot is equal to minus 2y by m, z double dot is equal to minus z by m. So these equations can be substituted in dlx by dt. That is, dlx by dt can be written as my into minus z by m minus z into 2y by m into m. That is minus my z by m plus 2y z m by m. That is equal to 2y z minus y z, that is equal to y z. Similarly, we can calculate dly by dt, that is equal to m into z x double dot minus x z double dot, that is equal to m z. Substituting these values of x double dot, we get m z into minus 2x by m minus m z dot minus z by m, that is equal to minus 2x z plus x z is equal to minus x z. dlz by dt is equal to m into xy double dot minus y x double dot is equal to m x into minus 2y by m minus my into minus 2x by m, that is equal to minus 2xy plus 2xy is equal to 0. That is dlz by dt is equal to 0. That means Lz is a constant. So here the question is asking about which component of angular momentum is constant. So here proves that to find which constant of motion is, which is the constant of motion, we had calculated dlx by dt and dly by dt and dlz by dt, and we calculated that dlz by dt is equal to 0. That means Lz is constant. So the option D is right answer, because only Lz is the constant here. So the next question is, a particle of unit mass moves in the xy plane in such a way that x dot of t is equal to y of t and y dot of t is equal to minus x of t. We can conclude that it is in a conservative force field which can be derived from the potential. Here we need to find the value of V. See potential. So here we have given x dot is equal to y dot is equal to minus x. From here we can calculate x double dot, that is equal to y dot. So we know x dot is equal to y. So substituting these values in x double dot, we get x double dot is equal to minus x and y double dot is equal to minus y. So the equation can be written as x double dot plus x is equal to 0 and y double dot plus y is equal to 0. So we know fx is equal to mx double dot, that is equal to, here it is given the mass is unit mass, so that the mass is 1. So fx is equal to m into x double dot, that is equal to 1 into minus x, that is equal to minus x, and fy is equal to my double dot, that is equal to 1 into minus y, that is equal to minus y. Then fx is equal to minus dou v by dou x is equal to minus x, and fy is equal to minus dou v by dou y, that is equal to minus y. From here, by integrating the value of fx, we can find v is equal to integral over x dx plus f of y, that is equal to x square by 2 plus f of y. And by differentiating this equation, we get dou v by dou y is equal to d by dy of f of y, that is equal to y. That means f of y is equal to integral over y dy plus c, that is equal to y square by 2 plus c. So substituting these values in equation number 1, that is v is equal to x square by 2 plus y square by 2 plus c. So the option is A. So the next question is, the dynamics of a particle governed by the Lagrangian L is equal to half m x dot square minus half k x square minus k x x dot t describes dash. Here the Lagrangian is given as L is equal to half m x dot square minus half k x square minus k x x dot t. That is, dou L by dou x dot is equal to mx dot minus k x t, and dou L by dou x is equal to minus k x minus k x dot t. From here we can calculate the equation of motion as d by dt of dou L by dou x dot minus dou L by dou x is 0, that is equal to mx double dot minus k x dot t minus kx plus kx dot t is equal to 0, that is equal to mx double dot is equal to 0, and this corresponds to the equation of the free particle, because we know in free particle there is no potential energy. So the equation of motion can be written as mx double dot is equal to 0. So the correct answer is option D. Here the other options are wrong, because for an undamped simple harmonic oscillator the equation is like this, that is mx double dot plus kx is equal to 0, but here we get the equation as mx double dot is equal to 0, so that it is not an undamped simple harmonic oscillator. And for a damped simple harmonic oscillator there should be a term that is proportional to x dot. There is no such term here, so that it is not a damped harmonic oscillator also. So the only option that is correct is option D, that is it explains about the free particle. So the next question is, the motion of a particle in one dimension is described by the Lagrangian L is equal to half into dx by dt the whole square minus x square in suitable units. The value of action along the classical path from x is equal to 0 at t is equal to 0 to x is equal to x naught at t is equal to t naught is dash. So here the solution is L is equal to half x dot square minus half x square. From here the equation of motion can be written as d by dt of dou L by dou x dot minus dou L by dou x is equal to 0, that is x double dot plus x is equal to 0. So here the solution is x is equal to a sin t plus b cos t. At t is equal to 0, x is equal to 0. So substituting this in the above equation we get b is equal to 0, that is x is equal to a sin t, and t is equal to t naught, x is equal to x naught. So the equation 1 can be written as a is equal to x naught by sin t naught. So the equation 1 can be written as x is equal to x dot by sin t naught into sin t, that is x dot is equal to x dot is equal to x naught by sin t naught into cos t. From here we can calculate the value of s, that is action, is equal to integral over 0 to t naught into L dt, that is equal to integral over 0 to t naught into half x dot square dt minus integral over 0 to t naught into half x square dt, that is equal to half x dot square cos sin square d naught integral over 0 to t naught into cos square t dt minus half x naught square by sin square d naught integral over 0 to t naught into sin square t dt. This is equal to half x naught square by sin square t naught into integral over 0 to t naught cos square t dt minus integral over 0 to t naught sin square t dt. This is equal to half x naught square by sin square t naught into integral over 0 to t naught cos 2t into dt, that is half x naught square by sin square t naught into sin 2 t naught by 2 t naught, that is half x naught square by sin square t naught 2 sin t naught cos t naught by 2, that is equal to x naught square by 2 cos x naught square by 2 cot t naught. Next question is, which of the following terms when added to the Lagrangian of a system with 2 degrees of freedom will not change the equation of motion? Here we need to calculate which of that which among these options added to the L doesn't changes the equation of motion. That means to check each option for this. So let me take the option B, that means x y double dot minus y x double dot. If we add this term to L, that is L dash is equal to L plus x y double dot minus y x double dot, and from here we can write the equation of motion as d by dt of dou L dash by dou x dot minus dou L dash by dou x. Now L dash is equal to L plus x y double dot minus y x double dot. So by substituting, by differentiating L dash with respect to x dot and x and substituting, we get dl by dt dt of dou L by dou x dot minus y double dot minus dou L by dou x. Equation, it says that the Lagrangian L satisfies the equation of motion, that is the Lagrangian L satisfies the equation of motion means d by dt of dou L by dou x dot minus dou L by dou x is 0, that is d by dt of dou L by dou x dot minus dou L by dou x dot is equal to dou L by dou x. Substituting these values in the equation, we get dou L by dou x minus dou L by dou x minus y double dot is equal to 0, that is y double dot is equal to 0. This can also be written in the terms of y, that is d by dt of dou L dash by dou y dot minus dou L dash by dou y, that is equal to 0. So this can be written as d by dt of dou L by dou y minus x double dot minus dou L by dou y.
And we know that d by dt of dou L by dou y dot minus dou L by dou y is equal to 0. That is d by dt of dou L by dou y dot y dot is equal to dou L by dou y. That is dou L by dou y minus dou L by dou y minus x double dot is equal to 0. That is x double dot is equal to 0. If we add this option B to the Lagrangian value, we know the Lagrangian already satisfies the equation of motion, and if we had this B term, B option to the L value, we get L dash, and this L dash also satisfies the equation of motion. That means the option B is the right answer, because if we add that option B to the L, we get L dash, and this L dash also satisfies the equation of motion. So the option is B is the right answer.
Question is the Hamiltonian of a system with 10 degrees of freedom is given by h of q1, q2, etc. up to qn, p1, p2, etc. up to p and t with an explicit dependence on time t. Which of the following statement is correct? So we need to find which statement is correct. So coming to B option says that H always represents the total energy of a system and is a constant of motion, but it is wrong, because H represents the total energy only if it doesn't have an explicit time dependence, and if the generalized coordinate are time independent and potential energy is velocity independent. So option B is wrong. And option C, that is Q dot is equal to dou H by dou Pi and P dot is equal to minus dou H by dou Qi, is valid in all cases whether it has an explicit time dependence or not, because it doesn't matter whether it has an explicit time dependence or not. The Hamilton equation is valid in all cases. So the option C is also wrong. Then option D says that any instant volume element in phase space remains unchanged in magnitude under time evolution. It means this statement is actually, this is the Lively's theorem, because any initial volume element in phase space remains unchanged in magnitude under the time evolution. This is basically talks about the Lively's theorem, but it is valid only if the system is conservative. But here it is given that the Hamiltonian has the explicit dependence, so that here the system is not conserved. So if the system is not conserved, then the Lively's theorem is not valid here. So option D is also wrong. Then coming to A option. Option A says that different phase trajectories cannot intersect each other. Actually, this option is correct, because if two phase trajectories intersect each other, it would meet at a point of intersection, and at a point of intersection, if the two trajectories meet at a point, we should have two set of q and p values. Actually, this is not possible, so that we can say that two trajectories never intersect each other, so that the option A is correct. Next question is, if the Lagrangian of a particle moving in one dimension is given by L is equal to x dot square by 2x minus v of x, the Hamiltonian is dash. Here we need to find the Hamiltonian from Lagrangian. So here we know that the generalized coordinate is x and their momentum is px. So here we can write h is equal to px x dot minus L, that is equal to also we have given a Lagrangian. So from there we can calculate dou L by dou x dot, that is equal to px. That implies x dot by x is equal to px, that is x dot is equal to pxx. So substituting these values in the Hamiltonian, we get h is equal to px x dot minus x dot square by 2x plus v of x. That is h is equal to px into pxx minus pxx by 2x into pxx plus v of x. That is h is equal to px square x by 2 plus v of x. So that the option is A. The next question is, the Hamiltonian of a relativistic particle of rest mass m and the momentum p is given by h is equal to square root over p square plus m square plus v of x in units in which the speed of light c is 1. The corresponding Lagrangian is dash. So here we need to find Lagrangian from Hamiltonian. So here h is equal to square root over p square plus m square plus v of x. Then dou h by dou px, dou p is equal to x dot, that is equal to half into 2p by p square plus m square the whole raised to 1 by 2, that is x dot into p square plus m square the whole raised to 1 by 2 is equal to p. That is p is equal to x dot m by square root over 1 minus x dot square. Then we know that L is equal to summation over x dot p minus h, that is x dot p minus h is equal to x dot p minus square root over p square plus m square minus v of x. Putting the value of p is equal to x dot m plus square root over 1 minus x dot square in the above equation, we get the Lagrangian as L is equal to minus m into square root over 1 minus x dot square minus v of x. This question is, a particle of mass m and a coordinate q as a Lagrangian L is equal to half m q dot square minus a lambda by 2 q dot square, where lambda is a constant. The Hamiltonian for the system is given by dash. So here Lagrangian is given and we need to find the Hamiltonian. That is h is equal to q dot p minus L, where L is equal to half m q dot square minus lambda by 2 q dot square. From here we can calculate dou L by dou q dot, that is p, that is equal to m q dot minus lambda q dot, that is p is equal to q dot into m minus lambda q, that is q dot is equal to p divided by m minus lambda q. Then h is equal to q dot p minus L, that is p square by m minus lambda q minus half m q p square by m minus lambda q the whole square plus lambda by 2 q p square by m minus lambda q the whole square. So this is equal to p square by m square minus lambda cube minus p square by 2 into m minus lambda cube the whole square into m minus lambda cube. That is equal to p square by m minus lambda cube minus p square by 2 into m minus lambda cube. That is h is equal to p square by 2 into m minus lambda cube. Next question is, the Hamiltonian of a one-dimensional system is h is equal to xp square by 2m plus half kx, where m and k are positive constant. The corresponding Euler-Lagrange equation for the system is dash. It is given that h is equal to p square by 2m plus half kx. Dou h by dou p is equal to x dot, that is xp by m is equal to x dot, that is p is equal to mx dot by x. Then L is equal to x dot p minus h. Then L is equal to x dot p minus xp square by 2m minus half kx. That is equal to mx dot square by x minus mx dot square by 2x minus half kx. That is equal to mx dot square by 2x minus half kx. From here we can calculate the Euler-Lagrange equation as d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. That is mx double dot by x minus x dot by 2x square plus half k is equal to 0. That is 2x mx double dot minus m x dot square plus k x square is equal to 0. Next question is, the Hamiltonian of a particle of unit mass moving in the xy plane is given to be h is equal to xpx minus ypy minus half x square plus half y square in suitable units. The initial values are given to be x of 0, y of 0 is equal to 1, 1 and px of 0, py of 0 is equal to half, minus half. During the motion, the curve trace out the path trace out by the particles in the xy plane and the px py plane are dash. Here we need to find the curve that traces out by xy plane and the px py plane. Here it is given that h is equal to xpx minus ypy minus half x square minus half y square. That is x dot is equal to dou h by dou px. And px dot is equal to minus dou h by dou x, that is equal to minus px minus x, that is equal to x minus px. Then py dot is equal to minus dou h by dou y, that is equal to minus of minus py minus y, that is py plus y. X dot is equal to dou h by dou px, that is equal to dou by dou px of x px minus ypy minus half x square minus half y square, that is equal to x. And y dot is equal to dou h by dou py, that is equal to minus y. Then we need to check the motion in xy plane. To check the motion in xy plane, here we calculated that x dot is equal to x, that is dx by dt is equal to x, that is integrating this we get dx by dt, integral over dx by dt is equal to integral over dt, that is ln x is equal to t plus c1, that is x is equal to a e raised to t. Here, by the boundary condition given in the question, we can write that at x is equal to 0, sorry, at t is equal to 0, x is equal to 1, and t is equal to 0, y is also 1. So, applying this initial condition in x is equal to a e raised to t, we can write a e raised to 0 is equal to 1. That is a equal to 1. Then we can also solve in terms of y also, because we know that y dot is equal to minus y, that is dy by dt is equal to minus y. Integrating, we get l and y is equal to minus t plus c2. That is y is equal to b e raised to minus t. Applying the initial condition, we get b is also equal to 1. X is equal to e raised to t, y is equal to e raised to minus t. From here, we understood that y is equal to 1 by x, that is xy is equal to 1. That means motion in the xy plane is hyperbola. We need to find the motion in px py plane. That is, we had find out that px dot is equal to x minus px. Rearranging this, we can write px dot plus px is equal to x. That is, px dot plus px is equal to e raised to t, because x is equal to e raised to t. That is, dpx by dt plus px is equal to e raised to t. This differential equation is of the form of linear differential equation. So that is, for linear form, dy by dx plus p of x into y is equal to q of x, we can write the integrating factor mu is equal to e raised to integral over p of x dx. That is, the solution can be written as mu into y, that is, integrating factor into y is equal to integral over integrating factor mu into q dx plus c. That is, here the factor is e raised to integral 1 dt, that is equal to e raised to t. So the solution can be written as e raised to t into px is equal to integral over e raised to t into e raised to t into dt. That is, e raised to t into px is equal to integral over e raised to 2t dt. That is, e raised to t px is equal to e raised to 2t by 2 plus c1. Then applying the boundary condition, that is t at t is equal to 0, px is equal to half, that is e raised to 0 into half is equal to e raised to 0 by 2 plus c1, that is c1 is equal to 0. Then e raised to t into px is equal to e raised to 2t by 2, that is px is equal to e raised to 2t by 2 e raised to t, that is e raised to t by 2. Then similarly we can calculate py, that is py dot is equal to, we had calculated that py dot is equal to py plus y, that is py dot minus py is equal to y, that is dpy by dt minus py is equal to e raised to minus t. From here we can calculate the integrating factor as e raised to minus t, that is solution is e raised to minus t into py is equal to integral over e raised to minus t into e raised to minus t into dt plus c2, that is e raised to minus t into py is equal to e raised to minus 2 by minus 2 plus c2. Applying the boundary condition, that is at t is equal to 0, py is equal to minus 1 by 2, that is e raised to 0 into minus 1 by 2 is equal to e raised to 0 by minus 2 plus c2, that is minus half plus half is equal to c2, that is c2 is equal to 0. So the solution is e raised to minus t into py, which is equal to e raised to minus 2t by minus 2. That is py is equal to e raised to minus t by minus 2. That is minus half into e raised to minus t. That is that e raised to d is equal to 2px. So substituting these values in the equation, we can write py is equal to minus half into e raised to minus t, that is minus 1 by 2 e raised to t, that is equal to minus 1 by 2 into 2px, that is equal to minus 1 by 4px. That is px py can be written as, that is equal to minus 1 by 4. So this motion in the px py plane is also represent the hyperbola. That means the motion in the xy plane and the motion in px py plane traces out the hyperbola curve. So the answer is hyperbola. Both planes shows the curve hyperbola. Question is, if the Lagrangian of a dynamical system in two dimension is L is equal to half mx dot square plus mx dot y dot, then its Hamiltonian is dash. Here Lagrangian is given as L is equal to half mx dot square plus mx dot y dot, that is dou L by dou x dot is equal to mx dot plus my dot, that is equal to px. Then dou L by dou y dot is equal to mx dot, that is equal to py. From here we can write x dot is equal to py by m. Substituting these values in equation number 1, that is in the equation of dou L by dou x dot, we get py plus my dot is equal to px. That is y dot is equal to px minus py by m. Then here we know that here there is two generalized coordinate, that is x and y. So here we need to consider px and py also. That is h is equal to px x dot plus py y dot minus l. That is equal to px x dot plus py y dot minus half m x dot square minus m x dot y dot. Substituting all this value of x dot y dot in this equation, we get h is equal to px py by m minus py square by 2. So this is the answer. The next question is the Hamiltonian of a system with generalized coordinate and momentum is h is equal to p square q square. A solution of the Hamiltonian equation of motion is dash. Here a and b are the constants. H is equal to p square q square. By Hamilton equation of motion, dou h by dou q is equal to minus p dot. That is dp by dt is equal to minus 2p square q. So this can be written as equation number 1. Dou h by dou p is equal to q dot. That is dq by dt is equal to 2p q square. This can be written as equation number 2. So from equation 1 and 2, dp by p is equal to minus dq by q. Integrating, we can write ln p is equal to minus ln q plus ln a. That is pq is equal to a. This is equation number 3. From equation 1, dp by dt is equal to minus 2p square q. That is equal to minus 2pa. That is dp by p is equal to minus 2a dt. Integrating, we get integral over dp by p is equal to minus 2a integral over dt. That is ln p is equal to minus 2at plus ln b. Here b is a constant. P by b is equal to e raised to minus 2at. That is p is equal to b e raised to minus 2at. This is equation number 4. Substituting the value of 4 and 3, we get b e raised to minus 2at into q is equal to a. That is q is equal to a by b e raised to 2at. So the answer is equal to b e raised to minus 2at and q is equal to a by b e raised to 2at. Next question is the Hamiltonian for a system described by the generalized coordinate x and the generalized momentum p is h is equal to alpha xp x square p plus p square by 2 into 1 plus 2 beta x plus half omega square x square, where alpha, beta, omega are constants. Then the corresponding Lagrangian is dash. So here we need to find the Lagrangian. Here h is equal to alpha x square p plus p square by 2 into 1 plus 2 beta x plus half omega square x square. Dou h by dou p is equal to x dot. That is alpha x square plus p by 1 plus 2 beta x. This implies p is equal to x dot minus alpha x square into 1 plus 2 beta x. L is equal to x dot p minus h. That is x dot p minus alpha x square p minus p square by 2 into 1 plus 2 beta x minus half omega square x square. That is x into, that is substituting the value of p in the above equation, we get we get L is equal to x into x dot minus alpha x square into 1 plus 2 beta x minus alpha x square into x dot minus alpha x square into 1 plus 2 beta x minus x dot minus alpha x square the whole square into 1 plus 2 beta x the whole square divided by 2 into 1 plus 2 beta x minus half omega square x square. So this can be rewritten by taking 1 plus 2 beta x into 1 minus alpha x square common. That is that is L is equal to 1 plus 2 beta x into x dot minus alpha x square into x minus alpha x square minus x dot minus alpha x square by 2 minus half omega square x square. That is equal to 1 plus 2 beta x into x dot minus alpha x square into x dot minus alpha x square the whole square by 2 minus half omega square x square. That is equal to 1 plus 2 beta x into x dot minus alpha x square the whole square by 2 minus half omega square x square. Question is, a point mass m is constrained to move on the inner surface of a paraboloid of revolution x square plus y square is equal to a z, where a greater than 0 is a constant. When it spirals down the surface under the influence of gravity, the angular speed about the z axis is proportional to dash.
So here we need to find the proportional term to the angular speed. Here the z term is mentioned, so we can say that here also we use the cylindrical coordinates, that is L is equal to half m r dot square plus r square theta dot square plus z dot square minus mg z. So here the constraint given is x square plus y square is equal to az, that is r square is equal to az, that is z dot is equal to 2r r dot by a. Substituting these values in the equation of L, we can write L is equal to half m r dot square plus r square theta dot square plus 2r r dot by a the whole square minus mg r square by a, because z is equal to r square by a. From here we can say that theta is a cyclic coordinate, and we know that dou L by dou theta is equal to 0 here. Then dou L by dou theta dot, which is equal to L, that is from here we can find the value of dou L by dou theta dot as mr square theta dot, that is equal to j. That is j is equal to mr square theta dot. From here we understood that the theta dot, that is the angular speed, is proportional to 1 by r square, and we know that z is proportional to r square, so we can say that theta dot is proportional to 1 by z. Next question is, a particle in one dimension execute oscillatory motion in a potential v of x is equal to a into x, where a greater than 0 is a constant of appropriate dimension. If the time period t of its oscillation depends on the total energy E as e raised to a, then the value of a is dash. So here we need to find the power of E. The potential V is given as Ax, so the total energy can be written as E is equal to P square by 2m plus A into x. The graph of the total energy can be drawn like this. From here we can say that at P is equal to 0, that means at momentum is equal to 0, E is equal to Ax, that is x is equal to E by A. Then at x is equal to 0, E is equal to P square by 2m, that is P is equal to square root over 2me. Like this way we can draw the graph of P versus x and U versus x. And from here we can calculate the value of J, which is equal to, we know that the x value changes from 0 to e by a, so that the integral term j, the integral limits of the j is equal to 4 into integral over 0 to e by a into square root over 2m into e minus ax into dx, calculated from equation 1. This can be rewritten as j is equal to 4 into square root over 2me integral over 0 to e by a into 1 minus ax by e square root into dx, that is equal to 4 into square root over 2me integral over 0 to 1 into square root over 1 minus t, because here we substitute a by e into x is equal to t, that is dx is equal to e by a into dt. Then when x is equal to 0, t is become 0, and when x is equal to e by a, t become 1, so that the integral limits changes from 0 to L, so that j is equal to 4 into square root over 2me integral over 0 to 1 square root over 1 minus t into e by a dt, that is 4 into square root over 2m into e raised to 1 by 2 into e by a square root over integral over 0 to 1 square root over 1 minus t into dt. Substituting x naught is equal to 4 into square root over 2m by a integral over 0 to 1 into square root over 1 minus t into dt, we can write j as x naught e raised to half e raised to 1, that is j is equal to x naught e raised to 3 by 2. From here we can calculate the time period as dou j by dou e, that is 3 by 2 x naught e raised to 3 by 2 minus 1, that is 3 by 2 x naught e raised to 1 by 2. So from here we can we understood that the time period is proportional to the e raised to 1 by 2, then the power of E is half. So that we can say the value of A is half. The answer is half.
So this is the end of this video. Thanks for watching this channel.